Hello everyone, welcome to the 4th edition of Math 262, Coronavirus Edition. It is March 19th, and as always I want to remind you that there is a WebAssign homework due on Friday. You have all the material to do it right now. And I want to remind you to upload your notes each day onto Moodle so you get a completion grade for that. Alright, so today should be an easy day. What we want to talk about is a topic that is related to the alternating series test. So, if you recall from last time, we saw that we had the series this series converged. But if I remove the alternating part, the series on the right diverges. It's not hard to show that -1 to the n plus 1 over n squared also converges by the alternating series test, and we know that the series on the right, 1 over n squared, also converges. So what you're seeing is two different types of behavior. Sometimes, if your series is alternating, it will converge, but when you remove the alternating part, then it diverges, as in the above case. But below that, in blue, we see that both the alternating sum and the sum that is not alternating both converge. This gives us two new definitions that we need to learn about different types of series, and they're called absolute and conditional convergence. So, let's give us those definitions now. So, we say a series converges absolutely. And this is the series, the sum of the AN, if the sum of the absolute values converges. We say a series converges conditionally when the series converges but the series where you add up their absolute values diverges. And in the above case, we saw two examples of that. We saw that the sum of -1 to the n over n, this converges conditionally. But the sum from n equals 1 to infinity of -1 to the n plus 1 over n squared converges absolutely. So what I'm going to do is I'm going to work two examples, and then I'm going to give you several examples to work at home that you'll need to submit with your notes for grading. So let's do another example, and let's look at the series sum from n equals 1 to infinity of -1 to the n plus 1 over n times the natural log of n. Well, so we see that the limit of the ANs, which is the limit as n goes to infinity of 1 over n times the natural log of n, these terms clearly go to 0. And if I look at AN, it's pretty clearly bigger than an plus 1. Okay, and it's alternating. This tells us that this series converges by the alternating series test. Okay, now we need to look at the series that involves the absolute value of the terms. So if I look at this sum, that is, I remove the alternating part, you can look back in your notes. You actually calculated this before. This series diverges, but you need the integral test to show it. So what this tells us is that our series, our original series, converges conditionally, because the series converges, but the series where you look at the absolute values diverges. Okay, I'm going to do one more example, and then we can continue. So, one nice fact about series is that if they converge absolutely, they must converge. So let's look at the series right here. The sum from 1 to infinity of negative 1 to the n plus 1 of n to the 4th third over n to the 4 thirds. Now, we know that the sum of 1 over n to the 4 thirds, this converges by the p-test with p equal to 4 thirds, which is bigger than 1. So this tells us that the sum of the absolute value of the terms of my series converges. In fact, that just tells you that the sum of my original series converges absolutely. Okay, so this gives us a bit of a flow chart for what we need to do. So let's say we have a series of this form, and we want to know, does it converge conditionally, diverge, or converge absolutely? So we have two cases. So the first case is if the sum of the absolute values converges. This tells us that our original sum converges absolutely. If the sum of the absolute values diverges, we have two more cases. One, if the sum of the ANs converge, this tells us that the sum of the ANs converges conditionally. And if the sum of the ANs diverges. Well, that's all there is to say. The sum diverges. So that we see is our flowchart that we can use to determine whether it converges absolutely, conditionally, or it diverges. And you see here we have the different conclusions that we can make. All right, excellent. So the last thing I want to do is to give you a few series, and you need to determine, using whatever methods you can, if they converge absolutely, they converge conditionally, or they diverge. So you'll need to do the work and submit it with your notes. So here are the series I want you to investigate. You might need to use a couple techniques. You might need to use a direct comparison test, or an integral test, or a limit comparison test. What we hope what you learn from this is to slowly recognize how each series I give you should, make you think of a particular kind of test. So, good luck, and let me know if you have any questions. Remember, if you have any questions about the alternating series test, to post the question or reply to someone else's question in the forum. All right, take care.